I'm Tom Ptacek, and we are here today to talk about detecting virtualized rootkits. To my right are my other research team members. This is Nate Lawson over here. Nate Lawson, formerly of Cryptography Research, the author of the unbreakable BD Plus Blu-ray DRM standard, which you should ask him about because it's actually quite cool. And Peter Ferrie, AV researcher from Symantec. The three of us jointly have been spending the last 9 months or so working with research that my former Matasano colleague Dino Daizovi, who I wrangled into sitting next to us for no apparent reason, did last year on the Vitriol hardware virtualized rootkit, which we'll talk more about in a second.
And Tom is from Matasano, a services firm, and they do a lot of work with enterprises clients. And this all sort of came out of a conversation we had last year together after the Vitriol and the other virtualized rootkit discussion about how we go about detecting these. And so here's the results.
So we did actually rehearse this talk, but I feel like the more I rehearse things, the worse I do in actual talks. So the one thing you're not supposed to do in a talk is apologize before the talk about the talk, and here we go. So let's start really quickly just by talking about what we're going to talk about in this particular talk. This will take us just a few seconds. So what we want to do is we want to give everyone in the audience a recap on how hardware virtualized rootkits work. This is the idea that underpins the Blue Pill hardware virtualized rootkit, and Joanna will be somewhere in the audience. You can raise your hand and I can introduce her. Hey. Somewhere in that direction. We applaud, by the way. It's fantastic work. So I want to explain how this stuff works as quickly as we can to get to the meat of how we're doing detection. Then we want to make... Can you hear me? Sound check?
Test.
Yeah. Am I fine now or am I not fine? Still not fine? You know what? It's too far away from my Utah while I fix.
Okay, so I'll cover this real quick. We're going to cover how Blue Pill works and how basic VT rootkits work. Vitriol, we're going to explain why nothing is 100% undetectable. There's always something you can observe in a system. We'll talk about our implementation of a test framework and the particular tests we used that allowed us to issue the rootkit challenge. And then finally, we're going to talk about where this is all going to end up in, say, 10 years, where basically you're stuck in a cat and mouse game, and it's exactly like the AV ecosystem we have today.
Let's try again. Any better at all? I assume so. You can raise your hand again if I'm totally inaudible. So, like we said, to start with, we want to talk about how hardware virtualized malware works. In particular, how our hypervisor rootkit, Vitriol, from last year functions, and then what we understand to be the differences between our hypervisor rootkit and Joanna's hypervisor rootkit. So, to start with, we want to put this in context. So, there's been an arms race of stealth malware, of rootkits and of viruses trying to hide themselves from detection code for as long as we can remember. You go back to the early 80s and there's that famous apocryphal story about the compiler backdoor, which when it compiled the login program would inject a backdoor into the login program. And when the compiler compiled itself, it would insert the compiler backdoor into the compiler, which, by the way, is far more clever of an attack than almost anything, maybe save Joanna's work. Far more clever than most of what we see from malware authors today. But this arms race proceeds through, for instance, Dark Avenger and the MTE polymorphic viruses stuff. So we had polymorphic viruses and, after that point, so we entered the epoch of much harder to detect viruses. In the 90s, we had kind of a race through the rings of the operating system, starting with HideSource, the original Solaris rootkit, which simply backdoored the login program, a userland binary, and kind of proceeded through KVM, the interface that userland uses to speak to the kernel. And from there into the kernel itself with things like Josh Damont's emodload, which actually built an entire new module loading interface into the closed source Sonos kernel. So we've seen this notion of kernel malware and kernel rootkits, things that insert backdoors into computers but use the operating system or the capabilities of the environment to hide themselves, going way, way back. And that goes through the late 1990s with the IAT rootkits and the SSDT rootkits and backorifice and
One of the key things here is that we've seen this before. We've seen someone claim the sky is falling, there will be some kind of rootkit that won't ever be able to detect It'll be in the kernel. You won't be able to do anything about it. And people have always found countermeasures, and we expect this is going to continue the same way.
So getting into the actual technical detail right now, one of the things that I want to make clear to you is that the way hypervisor rootkits work, or hyperjackers work, differs from what you're probably thinking of if you're familiar with virtualization, but not familiar with hyperjacking and virtualized malware. So we have this concept of like what VMware does, where you have a guest operating system running completely contained by the virtualization environment. So it's not doing anything that isn't in some way, shape, or form controlled by the hypervisor. So you have the operating system effectively running on top of the hypervisor. And I think that last year when we introduced the notion of hypervisor rootkits, people kind of walked in with a misconception about how these things work, namely that what a hypervisor rootkit is a very slim hypervisor that you would install under the operating system, and that can install itself and uninstall itself on the fly. That's not really true. What we're working with is a concept that's slightly different from virtualization, and we call it hyperjacking. And hyperjacking is the idea of using the virtualization capabilities of your platform, in our case, the Intel VT instructions that allow Intel hardware to be virtualized, to set up a trap handler so you can intercept certain things that the operating system is doing with the hardware. This is different from what real virtualization is doing because you haven't taken over all of the hardware interfaces that the operating system is using to speak to the hardware itself. If you had to do that, you'd have a problem that was as hard as what VMware has to do. VMware is a multi-billion-dollar company with very smart engineers gradually replicating all the device driver stack used by the operating systems that they emulate. Hyperjackers don't do this. They're much smaller than that. Most of the operations that a hypervisor rootkit is dealing with are passing directly from the operating system to the underlying hardware.
So please elide this from your memory, the slide in the middle, because no one actually implements it this way because it would be an untenable solution.
So again, the native operating system is speaking directly to the hardware. Think of the hypervisor rootkit as in some way running alongside the native operating system and simultaneously punching the running operating system in the nuts. That's essentially what hyperjacking does. Now, if any of you guys are familiar with web application penetration testing, and this is a labored analogy, but I'm going to try it anyways. If you've ever tested a web app, right, well, you know that you don't have tools that are customized to every single web application you use. What you have is a web proxy in the middle, right? So most of the complexity in a web application lies in the endpoints when you're testing it. It lies in the browser, and it lies in the web server. And if you want to test that and find vulnerabilities and exploit vulnerabilities in web applications, what you do is you put a component between the browser and the web server that passes almost all of the operations for that web application directly between the browser and the web server. And what the proxy does is it allows you to pick and choose which operations to look at and which operations to modify. And in a web application, modifying means inserting a single quote in a field or something like that, right? Well, it's very much the same thing with the hyperjacker. Like I said before, the hyperjacker isn't getting in between the running operating system and all the different pieces of hardware running there. What it's doing is it's picking and choosing which hardware operations to intercept and to work with. But like in the web browser scenario, most of the complexity in this environment resides in the endpoints. And we're going to use that phenomenon here against virtualized malware. One other thing I want you to keep in mind is because the hyperjacker itself, because the virtualized malware like Vitriol, because that system doesn't implement all this logic, but instead passes it through, it's quite small and quite easy to implement. It's much less complex than you might think it is. So one of the things that made this so easy to actually infect other computers with was how small it was and how easy it was to load. Vitriol is less than 2,000 lines of code. It does very little. It's just that what it does is, pretty dangerous.
So I want to talk a bit about the level below the instructions. When you think about machine code and malware and stuff like that, most of the things you're thinking about are instruction level state. For instance, if you hook the SSDT, that's changing some instructions in memory and some tables and stuff like that. And this instruction set has a whole other computer implemented below it. Most people aren't aware of this because you don't work at this level, but if you're Intel or AMD or people like that, you're intimately concerned with this. Basically, every instruction you have is implemented as microcode. There's actually micro-ops and small instructions that are within the CPU. They're software updatable. Some BIOS updates contained signed microcode updates as well. And these microarchitectural details are then affected by the side effects and the various components that are used to implement these micro operations. For instance, things like the cache, instruction scheduling, branch prediction. All of these items are micro-architectural details that are influenced by the actual micro ops that are running within your CPU while it's executing instructions. And if you go below that layer, you even have a whole set of embedded hardware or external hardware peripherals that each have their own CPUs. A friend and I once tried to count how many CPUs you'd find in a typical desktop or laptop system. You got about 20 to 40, depending on the type of system, CPUs in there. You've got a CPU to run your display. You've got microcontrollers for your keyboard, mouse, power management. You've got basically your wireless chipset. Most of them commonly have like a MIPS or an ARM firmware on board. You have all these different complex computers within your computer, and you basically have like a chipset LAN within each computer. And you can use that against the hypervisor because the hypervisor isn't aware of the state of the peripherals unless it was intimately familiar with every peripheral and emulating it or potentially custom designed to trap a particular driver's access to that hardware. So what you end up with is an increasingly complex set of state which is contained within the chipset in the computer, which isn't visible at the instruction level, but you can observe side effects of that. And here in this loop of arrows, we show a typical VT operation where you're running a hypervisor and some instructions run, and you do something like RDTSC or CPU ID, which causes a VM exit. So that traps to sort of the VT component, VT microcode of your processor, which then decides whether or not, based on what trap flags are set, to jump to your VM handler. So we showed in this case it decided to virtualize it. You're trapping this particular operation. And that jumps back to instruction level execution. And it has some effects at the microarchitectural level. For instance, if you're virtualizing a read MSR, for instance, the read MSR instruction is actually not executed. Instead, the trap happens before the RD MSR is actually executed. And so it begins executing other instructions. And this is a nice low-level interface to the hardware, but it doesn't tell the hypervisor anything about what's going on below that level, at the chipset level, at bus level, hardware level, and other microarchitectural side effects that may occur because of this jump through the VM exit handler.
So let's talk really quickly about, with that detail in mind, and hopefully that helps you understand Vitriol a little bit better, how Vitriol actually works and what that actually looks like in the real world. What Vitriol does when it loads itself, Vitriol, our Intel VT rootkit, or Dino's Intel VT rootkit, what Vitriol does is it installs from a kernel module. So unlike Joanna, which we'll get to in a second, we didn't come up with a clever way to load it under Vista. From kernel mode, what it does is essentially it forks the processor, or it forks the machine into a guest machine and a host machine. And when we say fork, think of it like Unix fork. What you're essentially doing is you're taking the running context of the computer, the registers and the memory areas and things like that, and you're loading a separate guest operating system that shares exactly the same memory segments, the exact same state. So once loaded, the hypervisor and the guest operating system, and when we say guest, we now mean the hyperjacked version of OS X running. Once it's running, the hypervisor and OS X share the exact same memory. They're just code. They're regions of instructions that get called under different circumstances. Think of the hypervisor as a different kind of interrupt handler running on that computer, and then it's using VT to hide attempts to actually detect it. So one of the things that does is it allows Vitriol access to everything in the running operating system, which allows operating system level backdoors to run much simpler because it's essentially it's the same machine, the same memory, just running in two slightly different contexts. We introduced this idea of, you have user land in a conventional operating system which runs at a lower ring of privilege. So your user land is ring 3, right? And under that you have the kernel, which runs in ring 0 with direct access to the hardware. And what virtualization